Let me start this presentation by thanking my thesis supervisor, Dr. Alka Bhushan, Dr. Rupal Bhargava, and Dr. Ahmed from Liverpool John Moores University for guiding me immensely to complete this research. The title of the research is Doclad, which is abbreviation of Deep Open Class Log Anomaly Detection. This will be helping the IT operation team, the IT operator, for detecting anomaly and thereby preventing service disruption. Every aspect in our life today is dependent on some IT services or other. But when the service goes down, it leads to emergency. It has got a huge impact on individual, on business or society. And that is how log anomaly detection comes into picture to help IT operator to detect early symptoms and take preventive action. This is not new. There are decades of research work which has happened in this field, yet there are improvement areas which will be very much required by the IT operator. To understand the complexities involved, let us take an example of BGL application. The log is divided into two parts. One is meta, another is message. In the meta part, there is definitely going to be timestamp information. And it is very similar to a sequence of words, one word coming after another, where the natural language processing techniques are deployed. Here, instead of word, a line appears at a time with a timestamp. Another information in meta is also helpful, which is the alert level. Sometimes they are very direct and indicate information, the failure or anomaly very directly and easily. And sometimes they may not. For example, here the message shows that there is some exception occurred, but the alert level information has failed to indicate that. And sometimes it could be even subtle. No error message is here in this OpenStack second log, where we can see this number could potentially lead to some anomaly if it is very high. So therefore, it's a combination of such numbers, domain specific word like this, which normally do not have any meaning in natural language, or a sequence, mean time of log arrival could be high, leading to some anomaly, or even the order of the logs, if they are not in proper order, could lead to some anomalous behavior. All these makes log analysis very challenging and also interesting. Here is the summary of the literature review that I had done, and it clearly indicates one trend which is moving from template based parsing method to using raw log as the input to your model, and thereby all the latest work has adopted the raw log based input, and that actually reduces the information loss in the input processing phase itself. However, you can see in the next column, parameter value, there are only very few people who have attempted to retain it, and in fact in the raw log based input processing category there is only one which has tried to utilize this. Interestingly, like all other papers who have focused on deploying the latest technology transformer to identify the log patterns, OneLog has delivered a very high level of accuracy by incorporating parameter values but using some older technologies like convolutional neural network, relatively older I would say. However, OneLog was not able to fulfill some of the important requirement, and that is the categorization of anomaly. It was able to deliver whether it is anomaly or not. But you can correlate with any diagnosis process. For example, in healthcare, doctor won't be happy just to know whether the patient is ill or not. As the IT operator, we'd like to investigate, or we'd like to know what kind of anomaly it is, and that would actually accelerate the action which has to be taken related. And we see that it is only one, the log class, who tried to classify the anomaly but did not deliver any other features which are also equally important. It didn't have the capability to detect unknown, and on top of that it used a machine learning algorithm which had a limitation of scalability. Therefore, there is a clear gap in the research, in the existing literature, and that is what this thesis would like to fulfill. I was intrigued why the researcher have removed the numbers from the log at all. The arguments by the researchers were that it is a natural language processing technique which we are deploying to get meaning from the text. And there, number don't play any role. Number should play a role in a different manner, KPI-based anomaly analysis. However, to my surprise, I discovered that there are enough literature and evidence available that NLP has a strong ability to understand number along with the text. And when that ability comes into picture, then character-based CNN actually outperforms the latest workhorse of NLP, which is BART. Although the debates were mostly around supervised and unsupervised method, none of them was actually able to address the requirement we highlighted previously. Therefore, the objective for this research is very clear: to effectively utilize all the information present in the log, including the domain-specific words and numeric values, to categorize the different type of anomalies, and also to detect unknown. We found the existing work, one log, was able to address the part 1, which is feature extraction, including numbers inside it, and with a very high level accuracy. And the part 2, which is detection of known, categorization of the anomalies, as well as detection of unknown. This was never thought before in the log analysis domain, and it is that is how I inherited from other domain, which was for open intent classification, and that is applied here. So basically this thesis will combine these two pre-existing methods to fulfill the gap which is there in the current literature. Coming to the methodology, it starts with the data processing, where each character in the line is converted as a token, essentially a number, and a bunch of these lines are grouped together to form a log sequence. For this entire sequence, this label indicates what type of anomaly it is. Once the data is prepared, that data is fed into convolutional neural network operation. First step is to learn the characters. Second step is to learn the log line, including the characters. And that can be further expanded to have a better understanding. We basically pass in m number of lines having n number of characters inside each line. And that after the character embedding, each character gets converted as JC, which is the embedded representation of each character. That is when it is passed inside the convolutional neural network, 3 layers of it. It is actually feature map which you get from each of these characters, different features of each characters. Finally, a max pooling operation is done to extract most impactful feature of the characters is what is extracted from here. Then that is what is passed to the next level of convolutional operation. In a similar manner, m number of lines, m number of log lines, how they are represented as a single feature is done by this layer of convolutional operation. In the methodology part 2, once this model is available and features are available for each classes, centroid for each class is computed by a simple algorithm of adding all the feature for that class, dividing by the number of feature which is available for that class, gives the center of the class. Similarly, for all other classes, the centroids are calculated, and then the training starts to learn the radius. Imagine a boundary which exists for each of the classes, where the radius indicates that how large the circle should be so that it can correctly classify the known and the unknown. During the testing time, if a known data is given, its radius is again calculated, and then if the radius is lesser than the known radius for that particular class, it will be marked as known sample. For example, here it will be marked as K1 because it is lesser than R1. Similarly for others. But when unknown is introduced in the testing, then hopefully their radius will be higher than any of these known classes, and that's how they will be marked as unknown. This was achieved by a custom loss function which would balance the expansion of the radius The circle should not be too small, neither it should be too large. That is what is balanced by a loss function introduced with this. In our testing, where we started with a very less number of data without numeric character present inside it, we performed many experiments by increasing the data volume little bit at a time. And as we increased, all the hyperparameter needed to be changed as well. Very good scores obtained. In fact, at 5,000 sample size, the score reached to 100%. At the same time, there are several other cases where the number of samples were either too less or too high. They were not delivering good score for at open classification. So we incorporated number which was stripped off in the initial exercise and found that this constraint was over. Keeping the numbers and other characters in the log line, increasing the log line, which means retaining more information, helped us to overcome this constraint. All those scores also started improving here. Further, we did an experiment to mix the log and see whether they are able to detect or identify one log from another. For example, it was BGL. In the BGL log, HDFS was also introduced, and we found that HDFS anomaly classification was clearly done with 100% accuracy. However, there was no previous score for log anomaly with open class classification, so it could not be benchmarked or compared with any other scores. Visualization of feature helped us to understand why the score was less. For example, here we see that initially with only one epoch, the softmax classification reached a 100% score. But even then, there were certain classes like yellow class. This was little scattered. When the radius learning process started with very low radius value, the scores were also less. When it reached to around 5 marks, the score started improving and reached up to 65%. The reason for this low score can be explained as this, that with unknown data introduced, there are a lot of mix-up between other classes which are happening, making it difficult to identify the known and unknown. Whereas for the other cases where we have got 100% score, we find that the classes were very far apart, particularly the open class, where this particular open, the unknown class was far from both the known classes. That might have contributed to the high score. In future, as we would like to test this model with data having more number of classes. This data what we had did not provide enough number of classes to test. Secondly, the features were scattered. They are not cohesive enough. The classes are not compact. So we would like to possibly apply techniques which makes the feature space compact and thereby facilitating a more robust training. The impact assessment for numeracy was done only by keeping or removing number from the meta part. But what happens when you remove number from the entire log as a whole is yet to be seen. In conclusion, the objective which was set, which was to enable a model which can understand the numbers and domain-specific character efficiently, was achieved through the Gaussian deployment. Then providing additional information to the operator, apart from whether the log is anomalous or not, that was achieved. It also delivered the capability of detection of unknown through the open space classification, which was not applied before in the log analysis domain before. Model was evaluated and showed very good score, although the number of classes present in the log was very less, which is a scope for the future work to increase and see what happens. Finally, I want to again thank to the professors and the thesis supervisor and the audience for their time.